Ladies and gentlemen, let's continue. We've started with chapter 4, differential relations for fluid flow. And the paragraphs in the chapter is firstly the fourth one, acceleration. The second one, the differential equations for mass conservation. That is what we are busy with. And that is going to be followed by the mass conservations, the differential equations for linear momentum, angular momentum, and energy. And I hope we're going to finish all of that today. After that, there's a section on boundary conditions, stream functions, vorticity, etc. And we will do that with the next lecture. Okay, so let's continue with 4.2, the differential equations for mass conservation. We've started with that with a previous lecture. Unfortunately, we couldn't finish it, but I've just summarized some of the most important features of that. Firstly, the small control volume that we consider of dimensions dx, dy, and dz. We look at the mass flow coming in and the mass flow going out. Okay, the mass flow in is very easy. It is equal to the density multiplied by the velocity multiplied by the face area. The mass flow going out looks much more complicated. Where does it come from? It comes from the fact that when we look at differential differences over a distance dx and we've got a function, if dx is very small, then we can say that mathematical equation can be approximated very well with a linear equation. And if that is the case, if that value is equal to rho u, then that value here would be rho u plus the gradient multiplied by dx. If you want to check it with a simple equation, y is equal to 2x plus 1. If that is x equals 0, then that value should be equal to 1. Okay. This value here would be 1, that value plus the gradient, which is 2 multiplied by 3, which is equal to 7. So it's a very simple concept that is being used. Okay. We've done that the previous lecture in the x direction. So here is the x direction coming in, there is that term, and the x direction going out, that one. We do the same in the y direction going in, y direction going out, and also for the z direction. And the result would be 6 terms. But if we want to consider continuity, we have to take into consideration that this control volume, the mass of it might also change. Okay, it might not be full. If it is full, the control volume, then if you put in 3 kilograms per second, then 3 kilograms per second will go out. But if it is not full, maybe at time equals 0, and 3 kilograms per second is going in and 1 kilograms per second is going out, so the control volume level is there, then it means that the mass of the control volume is increasing at 2 kilograms per second until it's full. Okay, you agree? Okay, so for that reason, in chapter 3, you've got this term that takes into consideration the change of mass of the control volume. So this comes from chapter 3, the change of mass of the control volume plus the mass flow going out minus the mass flow coming in is equal to 0. And that is known as the continuity equation. And you've used that quite a lot up to now. So if we specifically look at this term, okay, something that I forgot to put in here, sorry, dV, the volume. So it is d rho dt multiplied by the volume. If we specifically look at this term, okay, then the integral of the control volume of d rho dt of dv, remember this v is not the velocity, we use v normally for velocity in this course, and that is why I indicate it like that, to indicate it is volume. Okay, now we can say that if this volume is very, very small, as it becomes smaller, it is a good assumption to say that the density is going to remain constant in the control volume. So although we might have a big change in density over many control volumes, if you make the control volume smaller and smaller and smaller, then over that control volume, the density is not going to really change. So we're going to say it is approximately equal to d rho dt of dV, the volume. Okay, and the volume is equal to d rho dt multiplied by dx, dy, dz. So the density is not a function of x, y, or z, and therefore we can take it out and make this approximation. Okay, now let's introduce this equation 1, or all those terms that we've done, let's introduce everything into equation 1. Okay, then we can say that d rho dt multiplied by dx, dy, dz plus rho u plus partial ddx of rho u dx multiplied by dy dz. Okay, and I'm not going to add all the terms here next to each other. What I'm going to do is I'm going to put the next term underneath this one, plus rho v plus partial ddy of rho v dy multiplied by dx dz plus rho w plus partial ddz of rho w dz dx dy. Okay, so this is the first term, the change in mass, plus what is going out. What is going out are these three terms that we've added here. Now it says minus what is going in. Okay, so the change in mass is equal to the mass flow going out minus the mass flow coming in, and that is equal to 0. So let's put in what is going in on this side. So it's minus rho u dy dz, also minus rho v dx dz, and minus rho w dx dz, and that is equal to 0. So the change in mass of the control volume, there it is, plus all the mass flow going out, those three terms, there they are, minus the mass flow coming in, those three terms there is equal to 0. Sorry, I cannot hear you. The last equation. The mass flow rate going out, this term here. Sorry, yeah. Okay, yeah, dy. Okay. Are you all with me? Okay. Okay, now let's look at simplifying it. If we look at this term, rho multiplied by u, it is multiplied by dy dz, minus rho u dy dz, so they cancel. So that term and that term cancels. You agree? Okay. Then also rho multiplied by v dx dz, so that term and that term also cancels. The same in the z direction, rho w multiplied by dx dy, rho w dx dy, so that those will also cancel. Furthermore, if we look at dx, dy, dz, here we've got dx, dy, dz. So that and that cancels. Dx, dy, dz. Dx, dy, dz. Okay. So the result is that this equation simplifies to d rho dt plus partial ddx of rho u plus partial ddy of rho v plus partial ddz of rho w, and that is equal to 0, and that is known as the continuity equation, the differential continuity equation, or the conservation of mass equation. Continuity equation or the conservation of mass equation in a differential form. We can write it in a compact form by saying it is equal to d rho dt plus the grot multiplied by rho v in a compact form. You will see later why we prefer to write these equations in a compact form, especially when we start getting to the momentum equation and the energy equation. The terms are becoming quite a lot to write down, so it is just easier and more compact to write it like that. Okay. Now there are two special cases of the continuity equations. Two special cases. And it all has to do with assumptions. The first one is for steady flow. For steady flow. Let's look at this equation, d rho dt plus d rho u dx plus partial rho v dy plus partial rho w dz is equal to 0. Okay, so it is just that equation written down. And now we're going to look at the special case for steady flow. What does steady flow mean? Steady flow means that, and we are specifically interested in this term because this is the only one where the differential is to time. Okay. So if we look at density as a function of time, and it's a constant, then that term is going to disappear. Okay. So for steady flow, this equation reduces to partial rho u dx plus partial rho v dy plus partial rho w dz is equal to 0. So that is the first special case. The second one is for incompressible flow. For incompressible flow. Again, let's look at the equation, d rho dt plus partial rho u dx plus partial rho v dy plus partial rho w dz is equal to 0. Okay, what does incompressible mean? Incompressible means And it again has to do with the density. If we consider the density in the control volume as a function of, in this case, time and x, y, and z. Okay, x, y, and z. So everywhere in our grid, in all our control volumes, if we measure the density, then it's a straight line. Okay. So if that is the case, then firstly, that term will disappear because it's a constant, therefore the gradient is equal to 0. But those three densities will be constants. So therefore, we can say it is rho multiplied by du dx plus rho, it is a constant, so we can take it out, dv dy plus rho dw dz is equal to 0. If we divide right through with rho, the result is partial du dx plus partial dv dy plus partial dw dz is equal to 0. Okay, so that is for incompressible flow, and this one is for steady flow. Two special cases of the continuity equation. Now, although we have derived these equations in a Cartesian coordinate system, they can also be derived in other coordinate systems, for example, cylindrical or polar coordinate systems. We are not going to do that. It is in literature, the concept is exactly the same. But for example, in a cylindrical coordinate system, where usually we've got z perpendicular in this direction, that would be the velocity in the radial direction, in the tangential direction, and in the z direction. Okay. Three velocity components. And then this continuity equation, this one, can be written, and it will look like this, d rho dt plus 1 divided by r ddr of rho density, the radial velocity, plus 1 divided by r dd theta of rho, the velocity in the tangential direction, plus partial ddz of rho vz is equal to 0. Okay. In your textbook, the cylindrical one is given. There are other textbooks that would give it for you for other coordinate systems, for example, the spherical coordinate system also. Okay, the continuity equation are in practical problems usually used where, for example, we've got a tube or a conduit, and obviously we've got the inlet mass flow, and we would like to determine things, what happens on the outlet. The density might change, and we can determine the velocities. In CFD, we discretize the field, and in the field, we would like to solve these equations for every control volume. But they can also be used to test equations with. As an example, problem 4.12 in your textbook. So it's problem 14.12 in white, the 7th edition. Okay. And the flow field that is given is a very, very simple flow field. So the flow field is given by u is equal to x and v is equal to minus y. And the question is continuity satisfied by this equation or by this flow field? So we would like to know, is continuity satisfied? The flow field is given. Remember, when we started with this lecture, it was stated to you that if you've got the flow field, then usually you're very lucky. Then you know everything. In practice, usually you never have the flow field. This is now a very simple flow field. U is equal to X, V is equal to minus Y. And the question is continuity satisfied? Now, where do we start with a problem like this? I always believe we start with the fundamentals. The fundamentals is, this is the equation that has been derived, the continuity equation. So let's start with that equation. So the continuity equation says partial d rho dt plus partial rho u dx plus partial rho v dy plus partial rho w dz is equal to 0. The continuity equation that we have just derived. Okay. Now in terms of what has been given to us. What has been given to us is firstly, no information on the density. Density is not given. So let's assume rho is constant. No info on rho as a function of t. There's no equation that describes how the density changes as a function of time. So therefore we assume it is equal to a constant. Density is constant. Okay, if the density is constant, then and no other information is given on how things changes as time, we can also assume it is a steady state problem. Steady state. Okay. So no changes as a function of time. The density is a constant, so we can take the density out in all three the terms. Okay. And thirdly, no information is given on what is happening in the z direction. Okay, no information. There's no velocity in the z direction, and there's no z terms. So we are also going to assume it is a two-dimensional problem. Two-dimensional problem also. So if it's a two-dimensional problem, the densities are constant, then this equation reduces to partial du dx plus partial dv dy is equal to 0. Let's go through it again. If I look at what has been given, okay, very, very little information. It's given a velocity, which is in the x direction, and a velocity in the y direction. No information on the z direction. So it's reasonable to assume it's a two-dimensional problem. Okay. No information is given in terms of time. Nothing. So we can assume it's a steady state problem. If it's steady state, then that term disappears. Okay. Also, no information on the density. We therefore assume the density is a constant. If the density is a constant, then we can take it out. Okay. It's a two-dimensional problem, so that term has disappeared. The two densities we can cancel out, and the result is partial du dx plus partial dv dy is equal to 0. You happy with that? Okay. So if that is the case, then it's very easy to say that the u velocity is equal to x, so it is dx dx plus dv is equal to minus y dy should be equal to 0. Okay. dx dx is equal to 1. That is equal to minus 1. It is equal to 0. So we can say that this flow field satisfied the continuity equation, indeed. You agree? Okay. Let's do a next one. The next one, the flow field flow field is given as U is equal to sin square xy, and V is equal to cos square xy. We make the same assumptions. Again, U and V is only given as function of x and y. Nothing is given as a function of z, nothing as a function of time. So we can say that du dx plus dv dy is equal to 0. U is equal to sin square xy. So is d dx of sin square xy plus d dy of cos square xy should be equal to 0 if it satisfies the continuity equation. Okay, the differentiation of the first term would be 2 times the sin of xy, okay, multiplied by sin xy is then cos xy, and the differentiation is to x, so it is equal to y. That's the differentiation of the first term. You happy? 2 times comes in front, sin xy, the sin cos xy, and that in terms of x is equal to y. The next one, plus 2 times cos xy, multiplied the differentiation of cos is equal to minus sin xy, and here we differentiate to y, and the result is equal to x. And we can see it is not equal to 0. Okay. So we can say that this flow field does not satisfy the continuity equation. Any questions on the continuity equation before we continue to the linear momentum equation? Nothing? Okay. Paragraph 4.3, the linear momentum equation. The linear momentum equation. Again, let's consider a control volume in the x, y, and z directions. And what we're going to do in this case is the momentum equation is about forces. Sum of the forces is equal to the change in momentum. That is Newton's second law. So therefore, we're going to look at the forces and the changes in momentum. Okay. And we're going to consider, therefore, a force balance around the control volume. Now this force balance says the sum of the forces is equal to partial ddt of the control volume of the velocity vector rho dv. You've done that last year in the fluid mechanics course. So it's from your chapter 3. Plus the sum of the mass flows multiplied by the velocity going out minus the sum of the mass flows coming in. And let's call that equation 2. Okay. So that is coming from chapter 3. Again, we would say that this element is so small. Element is so small that we can say that this term, partial ddt of the velocity vector rho dv, the volume, is approximately equal to partial ddt of rho, the velocity dx, dy, dz. So it is so small that there's no huge gradients in terms of the density and the velocity vector. So we can say that that is approximately equal to that. Okay, now just like with the continuity equation, let's look at everything coming in and everything going out. In terms of direction, this would now be the inlet momentum and then the outlet momentum. In the x direction, the inlet momentum is now equal to rho u multiplied by the velocity vector dy dz. You'll see that things is going to start becoming more complicated now. And if you look at the study guide, you will see that it is expected of you for the test and exams to be able to derive the continuity equation, but not the momentum equation. But we need to know where it comes from, and we need to understand it a little bit. So in terms of the directions, the x direction, that is the inlet, and the outlet momentum would be equal to rho uv plus ddx of rho u v dx multiplied by dy dz. So that would now be in the x direction. In the y direction, it would be equal to rho v multiplied by the velocity vector dx dz, rho v multiplied by the velocity vector plus ddy of rho v multiplied by the velocity vector dy and dx dz. If you can't follow my handwriting, that is a little bit more neat. Okay. All the inlet momentum equations and the outlet momentum equations. Okay, now all these three equations, let's call that equation 3. And if we now look at this equation of the sum of the forces, then we can say it is equal to, after a little bit of manipulation, dx dy dz multiplied by partial ddt of rho multiplied by the velocity vector plus partial ddx of rho u multiplied by the velocity vector plus partial ddy of rho v multiplied by the velocity vector plus partial ddz of rho w multiplied by the velocity vector. So that is the sum of the forces, and at the end it is equal to rho dv dt multiplied by dx, dy, dz. How does that happen? Because if you go and manipulate some of these equations, you can actually get the continuity equation out of it, which is equal to 0. And that reduces it and makes it much smaller in terms of the resultant terms. Okay, so you go and manipulate these equations a little bit. You can see, take out the velocity vector, get the continuity equation, those three terms is equal to 0, and the result is that this equation can be derived. Okay. Now this is not the end of it. Usually it doesn't help us to know that in a big grid, the force on a control volume is equal to 2 Newton. Usually what we are interested in are the velocities. We want to know the velocities and the pressure. That is what we want. So what we did up to now is we've actually only looked at the right-hand side of the equation. We still need to look at the left-hand side of the equation, which also have a few terms. Okay, and these terms, the sum of the forces, can be divided into two categories. Okay, the one category is body forces. Body forces. Okay, your body forces are external fields, for example, gravity, magnetism, or electrical potential, working in on the control volume. The one that we in mechanical engineering are usually interested in is the gravity one. So that is the one that we normally work with. The surface forces is the other type of forces. Okay, the surface forces are the stresses on the control volume. The stresses on the control volume, and it's the sum of actually the stresses and the hydrostatic forces, which obviously includes the pressure. Now with the next lecture, we're going to look at these body forces in detail so that we can get the linear momentum equation in all its detail.